Hi guys, welcome back. In this video, I want to talk about how we can model mechanical rotation systems. So this is a single disc which is supported by some bearings. Okay, and we want to see how we can model this. Let's get into it. At first, I'm gonna list the elements in the system. For the elements, I would go after inertia, stiffness, friction, my source, and the number of bodies. Okay. Now, looking at this system, you see that since it's mechanical rotation, my inertia element is my mass moment of inertia. So J of the disk is the rotor, is the inertia element. In this problem, I do not have any stiffness element. There are no springs involved. Also, you notice that we are using viscous friction for the bearings. So I'm just going to include it as friction element. The source in this system is the external torque, which is coming from the motor. Okay, so I would consider the external torque as an input to the system. And the number of ODs, since I have only one independent motion, which is the motion of the disk, I would consider it as 1. Okay. With these, let's go to the 4-step approach and try to model the system. Okay. I'm going to start with step 1. Step 1 was selecting our coordinate system. Okay. Now, if you look at this setup, you see that theta is somehow given to you in a way that it comes out of the page. Yes? So if you look at the setup from the place that you are looking at it, okay, from the front view per se, you see that theta is actually going out of the plane. However, if you step aside and look at the system from the side view, then you see that theta is in fact going in clockwise direction. So that's what I will ask you guys to do, to step aside and look at the system from the side view, not front view. Okay. With this coordinate system, I'm going to go to step 2, which is isolating the mass, okay, or mass moment of inertia. Isolate our inertia element. Okay, what do I mean? I mean that grab the inertia element, disconnect it from the system, and throw it on a piece of paper. Okay, good. This step is done. Now I can go to step 3, which is the equation of motion. Sorry, which is the free body diagram. In step 3, again, I would go after view, CSR. Okay. The first one is friction. Now, I would need to look at 2 things here. The first one is the moments or torques. Okay. They are somehow given to me directly, or they are the reactions from the environment. Okay. For instance, you see that if I have a bearing, I would have a torque here. And sometimes it's not an explicit torque. It's basically a force and an arm which generates a torque for me. I need to account those ones as well. Okay? So for me, the friction is basically the viscous friction. Okay? And if I assume that the disk is going in the positive clockwise direction, my friction torque would be going opposite of the direction of motion. Okay? So if the direction of motion is clockwise, this is going to go counterclockwise. Similarly, the external torque is given to me. If you look at the setup, you see that T input is in fact given to you in the same direction of theta. So T input is actually going clockwise direction. Okay. Now, if you assume that the center of mass for this disk is actually the center of rotation, okay, you notice that weight is applied at the center of rotation. For a force to be able to generate a torque for me, it should have an arm. For instance, if weight was instead of being applied at the center of rotation, it was applied over here, that was a totally different story, because that force would have had an arm like this, okay, which the cross multiplication of that arm and force will generate a torque for me. However, anytime you see that a force is applied at the center of rotation, or the extension of that force passes through the center of rotation, those forces do not generate any torque for us. So weight does not generate any torque for me. I would neglect that one. Similarly, if you look at the contact force, for instance here, you see that my normal reaction from the surface is actually applied in a way that it somehow, extension of that force somehow passes through the center of rotation. Okay. For the same reason, since this force does not have any arm to generate any torque for me, I'm going to neglect that one as well. The next one is the spring. I did not have any stiffness element in the system, and there was no rope in the system. So my free body diagram for this system is complete. I can safely navigate to the next step, step 4, which is basically the equation of motion. Okay. Look at this. What I'm going to do is I'm going to just write down the Newton's second law for the torques. So the summation of the torques along theta equals to J theta double dot. Now, look at your free body diagram. How many torques do you have? You have one here and you have two here. Okay. So there are two torques, okay, which in this setup, you see that B theta dot is in fact in the negative theta direction and T input is in the positive theta direction. So I'll bring them down here with their signs. Yes, positive Tn, negative B theta dot equals to J theta double dot. Yes? Okay. Now, let's keep the input on one side, bring the dynamic terms to the other side. Then you will have T input equals to J theta double dot plus B theta dot. Okay. And you can do the sanity check for this setup. You see that you have only one family, which is the family of theta. Within that family, you have two members, theta dot and theta double dot. So there are no sign mismatches within the members of that family. You can safely box this equation. Good? Okay. So this was an easy example. Yes. If you look at the system, you see that this is a second order linear system. Yeah. Now, I have a question for you guys. Is it possible to reduce the order of this system and make it a first order differential equation or no? So let's pause the video for a moment and think about this, and then come back and get the answer. Okay, so yes, it's possible for this specific system. Note that if you consider omega as theta dot, then omega dot would be theta double dot. And if you substitute theta dot and theta double dot in the dynamics of the system, then you will have T input equals to J. Instead of theta double dot, I'm going to put omega dot. And instead of, it's going to be plus B, instead of theta dot, I'm going to put omega. Okay. Again, you see that I have one family, which is the family of omega. And within that family, I have two members, omega and omega dot. I would have no sign mismatches among the members of that family, yes? So I can safely box this equation. So this is the first order differential equation, which is basically, again, a linear system, okay? So note that, guys, when you solve this equation, you get theta. When you solve this equation, you get omega, which is the time derivative of theta, okay? So in a way, this second equation, which is the first order differential equation, does not give you the angle, but the first equation will give you the angle. So it really depends on what you're modeling. If you're modeling to find the velocity, okay, so maybe you can reduce the order of the system. However, if you want to find the angular position, then you need to go with the second order differential equation. I hope you liked the video, okay? And if you found this video helpful, please subscribe to the channel for more videos.